sequence phi in the n dual, right, such that if you restrict this phi to the submodule Mn, you'll get zero map. Okay, so then we can say that the 0 is equal to the phi Mn, right? I'm taking phi from this module. And so I know that it's on this submodule it is 0. Now, of course, this is a linear map, so I can write as well M phi of n. And so I can conclude that the quotient of the n modulo Mn with the check, this is precisely the SOCO of the n dual by this computation. Okay, so we know that the SOCO can be described as the same thing as the home from K to the module, right? In this case, well, this is SOCO of the dual module. These are all homomorphism. If this is from the K to the module, it's as well just a map from the ring to the module, such that, or element in the module, such that this element is annihilated by the maximal ideal. Here, this is exactly the element that's annihilated by maximal ideal. And of course, anything in the SOCO give us a map here. Okay, so the minimal number of generators over, so generators of n, over any local Napierian ring for a module which is finitely generated, and of course this is finite length module, this is finitely generated. I can compute this minimum number of generators as the dimension of the residue field of the n modulo Mn. Which is the same thing as the dimension of the dual. And since we just observed that this dual is the same thing as the SOCO, this is dimension of the SOCO of the n dual. But this dimension of the SOCO of the n dual is the R of the n dual. Yes, this is the proof of the first formula. And the second formula is just the first formula plus the duality in the...
Why is the dimension of the dual?
Yeah, why is there the second equality?
Yes.
Dimension of the dual? What?
The second equality.
This one?
Mm-hmm.
Well, this is you already know. This is this thing. Dimension of the residue field is exactly length. It's just another way to write the same thing. Right, what was length? It means that you can kind of construct your module from the simple modules in the so many steps that you have this number length, right? But each simple module is just K over local ring. So you can construct your vector space from the L of n one-dimensional vector spaces. So the length and dimension is the same. So when I need length, I write length. When I need dimension, I just write dimension.
Yeah, but is it true that n check quotient Mn check equal to n quotient Mn check?
No, I guess I'm just saying this exact sequence.
Probably, but I'm not so sure, because this sequence should be like kind of reversed. Ну, то есть, чтобы использовать что равенство, нам нужно, чтобы вот этот dimension, вот размерность n поделить, отрицать по mn check, она должна равняться размерности n check поделить,
No, we don't need anything. This is the module of finite length, and this is the module of finite length.
Yes.
And I know that the length of the module and its dual is the same, hence this.
We're doing it like that. Yeah.
So just direct application of the two here.
Yeah.
Explain why n modular mn check is this so-called n check.
I'll try to explain this. What are elements in the circle? Well, the formal definition, and it kind of works in very general algebra, is just a submodule generated by all the simple modules, or in other words, the maximal semi-simple submodule. But in this situation of the local ring, we know that there is one simple module, namely k, right? So the circle, you can as well write circle of some module n. You can write as a home from the k to the n. Right, so these are all possible simple modules, say all of this form, and namely these are just elements in the M which are annihilated by the maximal ideal.
Yes.
And you just take a module generated by all these elements. But you can see that this is precisely what we have in this module. This will be a map and elements in this module for which we try to compute the circle, which are annihilated by the maximal ideal.
Yes.
Okay. So I think that's the end of the proof. There's the second formula, very simple exercise. Use first formula and use the statements 2 and 3 to derive the second formula. More or less immediately follows. Okay. Next proposition. So in this case, I'm going to assume that Rm is not just a local Noetherian ring, but this is Artinian local ring. Or in other words, this is local Noetherian ring of dimension 0. As before, maybe I should stop writing this. E will be always the injective hull of the residue field. So then E is finite, faithful R module satisfying several properties. So the first is that the length of E is the same as the length of R. 2, R is isomorphic to the endomorphism ring of the E. And 3, the type of E is 1. And the minimal number of generators of E is the type of the ring. And conversely, any finite faithful R module of type 1 is isomorphic to E. And this happens a characterization of the module E. This conversely part will be needed later when we discuss Goldstein tricks. Okay. So the proof is relatively simple, right? So first of all, we can notice, if we look at the duality, that the E is the dual of the R, right? So this is home from the R to the E, so this is from the R to the E, we should just E. And since we assume this is Artinian situation, of course this is part 1. The length of the ring is finite, right? And then what we saying here is that, well, just by previous theorem, the length of the E is the same as the, say, length of the dual of E, which will be the length of the R double dual, which will be the length of the R, just immediately follows from what we've done before.
Yeah, everything just follows.
Yeah, well,
Second.
there are some things, well, for example, well, let's see, almost everything follows immediately from the previous, yes. Yeah, so here we have canonical map. For any module we have such map that from the R to the home. Well, I can write from E to E, but I can just as well write home from the R to the E and then to the E. Right? So this is the same as the canonical map from the R to the endomorphisms of E. Yeah, and this is an isomorphism, right? Since this is just the same home. This is from the R to the R double dual, which is an isomorphism, but I can interpret this first element, well, this is the same thing identically as the endomorphisms of E. So in particular from this we see that we see that E is faithful. Right? So faithful means that there is no annihilator, but the annihilator is just the kernel of this canonical map. So there is no annihilator. So this finishes 2 and faithful part. So 3 is more or less immediately follows from the previous proposition. Follows. Previous proposition. Okay,
Why is
so
it finite?
Hmm?
Why is it finite?
who n?
E.
E, well, for example, there's this formula that the length of E is the same as the length of R, so E is the module finite length, and any module finite length is finitely generated, finite. So there's this conversely part, so this is maybe requires a little bit of proof. So let now n be a faithful finite R module of type 1. Well, first of all, I claim that the length of n is finite without any computations. Do you see why the length of n is finite?
Because it's finite over an Archimedes ring.
Exactly. So length is finite. But for modules of the finite length, if we look at the minimal number of generators of the dual module,
Why the length is finite?
what?
Why the length of n is finite?
Oh, this is not generated,
Yes.
and the module is finitely generated.
Okay.
So instances of finite length. Yeah, so the minimum number of generators of the dual, this is the type of the given module, which is we know to be 1. So we know that the n dual is a cyclic module. And if this is a cyclic module, it is necessarily of the form R module some ideal. Okay, but since we have this duality, the reflexivity, we can write n, so module n is isomorphic to the home from the n dual, and n dual is just the R module I to the E. Right, so if we can write such formula, then we can say that the In is 0. So ideal I is annihilating everything in the N. But N is faithful. So the ideal is 0. And if the ideal is 0, the N dual and check is isomorphic to the ring, and hence the double dual, or N, is isomorphic to the dual of the ring, which is the E. Okay?
Why L is isomorphic to its double dual? Since this has finite length.
Mm-hmm. Okay. Well, so far we get all the results for modules of finite lengths. Let's go to a more interesting situation. So theorem. Let Rm be a local Noetherian ring. So then its completion is isomorphic to the endomorphism ring of the E, where E is, as before, the injective hull of the residue field. Well, so in particular, this gives us duality between the ring and the module E in the situation where we have a complete local Noetherian ring. Then we don't have to put completion since it's already complete, and we see that dual of E is R. This is why this is interesting and important for modules which are just, say, finitely generated or Artinian. Okay, the proof is some computation, but let me first set some notation. So let En with some index n be just all elements in the module E such that they are annihilated by the m to the n. So, or in other words, we can think about this as the home from the R modular m to the n to the E. So this is just some submodule of the module E. So I want to show that actually module E is the union of all such submodules. Well, if we take some element x in the module E, I want to show that this x actually belonging to En for some n. So, of course, I need to take x not to be 0, otherwise this is trivial. So then, the associated primes of the cyclic module generated by the x. Well, this is cyclic module, which is submodule of the E. So this set of associated primes is a subset of associated primes of the module E, which is just a set with one element, the maximal ideal. So in other words, the set of the associated primes of the cyclic module is just that with one element m. Well, m is associated to the Rx. It means that I can find an element R, little r in the ring R, such that the annihilator of the Rx is precisely m. So if I assume that R is in the m to the power n minus 1, well, maybe this is not a little bit unfortunate notation, but I'm just saying, well, R is belonging to some power of m. Maybe this is just the zeroth power, then this is not in the maximal ideal, this is just a unit, but maybe it's some higher power. So, if the annihilator of the Rx is m, so then we can say that m to the m annihilates x. Right? So, and if this annihilates x, that's exactly what I want, right? Then x belongs to the En, and hence E is the union.
Why element annihilates an x?
Well, the annihilator of this element is m, right? So the element of, well, if you, and r belonging to this power,
Yes.
so m r x annihilates.
Yes.
Yeah, but not every element in m to the power n looking like m multiplied by some, but it's this r. Ну, короче, не все элементы.
Ну,
Да.
Sure, but this is not a problem. I mean, this is just kind of for convenience, right? I know, well, that the worst possible scenario is that this R is a unit, right? Then M is still annihilating the X. So then X is still belonging to the En, which is in the E1 in this case. This is the worst possible case. And if this is not the case, well then this X is annihilated by this product. Well, if this is not just the maximal ideal, this is something smaller that sits in some power of the maximal ideal. That is what I'm trying to say. So definitely everything will be in E1, but maybe if this is not the unit, if this is already in some power of the M, this won't be E1, this will be E with some larger index n.
Сейчас вопрос, ну, если m принадлежит n в степени n-1, ну там n больше нуля, то тогда r принадлежит и максимальному идеалу, да? То есть мы, в принципе, можем доказывать просто для максимального идеала. Ну или для юнита.
Может, да. Но я просто пытался ввести индексы таким способом, чтобы в итоге вот получилось как бы правильно.
Я вот не понимаю, можно же взять n равно единице? Ну, любое r лежит в r.
Ну, тогда r это юнит.
M равно единице, я не понимаю.
n равно единице.
N равно единице можно?
И тогда утверждается, что m всегда аннулирует x.
Да.
А почему?
Ну, это просто...
Потому что m от аннулятора будет x тогда.
Нет, r не единица, но n равно единице. Он, может, r лежит в m, а я взял n
Да,
равно...
очевидно, что...
Нет, это же не имеет никакого смысла, то, что вы говорите. Вот это n, оно определяется по r.
Да, то есть это минимальное, максимальное n такое, что r.
Да. Well, anyway, so any element is one of the ENs. Yeah, and of course I want to rewrite this union in a tautological way as the co-limit, or I would rather say direct limit of these ENs. And now the computation. Let's look at the home from the E to the E. Well, I'm going to replace the first home by this direct limit. So then I can pull out this direct limit and get the inverse limit of the homes. Now for each individual En, I can plug in my formula with the home. So this is the home from the R modulo M to the N to the E, right? Okay, now we can notice here that what we have, it's not the correct formula. There is an argument missing. E and then again E. Yeah, okay. So this is just the double dual, the inverse limit of the R modulo M to the N double dual. But this module R modulo M to the N is the modulo finite length. Hence, this is isomorphic. And of course all this equality equalities before were just isomorphisms. Maybe this one is just equality. Okay, so this is just the inverse limit of the R modulo M to the N, which is by definition the completion of R. Okay, so corollary from this theorem is that if R is complete, so then the E dual is isomorphic to R, and of course R double dual is isomorphic to R. Okay. Proposition. So let Rm be a complete local Noetherian ring. So then we can show that E is Artinian. Okay, so let's assume that we have a descending chain. So P, let's say this is equal to N0, it contains N1, contains N2, etc. So this is a descending chain. So I want to show some sort of contradiction if this chain doesn't stabilize. Well, first of all, we can notice that the Ni is the submodule in the N0 for any I starting with 1, right? So then if we apply the duality to this, we will get that the R, which is the home from the N0 to the E, this we already know, right? So the home from E to E is R, has an epimorphism to the home from the Ni to the E. So what we see from here is that the dual of any of these submodules is actually a quotient of the ring, namely this is a secret module. So I can write any home from the Ni to the E as the R isomorphic, R modulo I with some index I. And then we will get a chain, now ascending chain of the ideals. So this is ascending chain of ideals of the ring R, which is assumed to be Noetherian. So we can find some positive n such that EI is equal to the EI plus 1 for any I greater or equal than n. So this is the stabilization of this chain. Okay, so now let's look at the following. We have Ni plus 1 is a submodule inside Ni, and there is some quotient. Right? So I'm assuming that I'm taking the short exact sequence with the same assumption on the I. So I is at least n. Right? So with this assumption, if I apply the duality, I'll get the following. I'll get that, let me try to write it here, 0. So then we will have home from the quotient I plus 1 to the E. And I know that the dual of the Ni is R modulo I with the index I, and the dual of the n with the index I plus 1 is the R modular I with the index I plus 1, which is an isomorphism. But this means that Ni modular Ni plus 1 is isomorphic to 0. Well, just jumping to conclusions a little bit, but this is 0, and E is an injective cogenerator, hence this module is 0. Okay? So in some sense, I think that's the end of the proof, because right, we proved that for any descending chain, we have this stabilization. Okay, so proposition, we have in the situation that we consider, again, the situation is as before, so let Rm be a complete local Noetherian ring. So then an R module is Artinian if and only if if and only an R module R module M is Artinian. I think I missed M. If and only if this R this M is finitely embedded. Which means, so that is M is the submodule in the E to the N. So maybe I just comment on this, that this is again a general algebraic conditional module. You can talk about finitely embedded modules over any ring, and that would be a modules which are submodules of a finite sum of injective house of simple modules. So, and what we have in this situation that we're interested in, the situation of the complete local Noetherian ring, we can characterize Artinian modules in a way kind of dual to the Noetherian modules, right? So in this situation, Noetherian module is the same as finitely generated, or in other words, this is a quotient of the R to the N, right? And this is completely a dual characterization. M is Artinian if this is a submodule of the E to the N. Okay, let's prove. So in one direction, if I assume that this is a submodule of the E to the N, this is clear. Right. And in the other situation, in the other direction, we have the following: the socle of the M that sits inside M, and this sits inside the injective hull of M. So both of these inclusions are essential extensions. So this whole inclusion is just an essential extension. And this means that the injective hull of the module is the same as injective hull of the socle of the module. But the socle of the module is just some finite dimensional vector space. So this is E of the K to the N. So we proved this on the seminar, that this is isomorphic to the E to the N. End of the proof. Okay. Maybe it was two big questions.
Yeah, injective hull commutes with
Direct sums.
direct sums.
Yeah, we proved this. There was a proof on the seminar. last problem on the seminar.
Yeah, and we prove that injective hull of Sokol is the same as injective hull of.
I just proved right here.
Why is it essential? Since.
Well, this is the essential extension, right? And this is injective. Hence, by definition, this E of M is the injective hull of the Sokol of M. So, and this is essential extension. We proved this last week. For any Artinian module, Sokol inside module is essential extension. But maybe you should ask why the Sokol is finite dimensional. I think this is the only non-trivial claim here. Do you see why the Sokol is finite dimensional vector space for Artinian module? No, what if this is not finite dimensional? Well, what if you?
M is not Artinian.
Yeah. So what if you construct a chain such that you kind of choose a subspace of codimension 1, choose a subspace of codimension 1, etc., etc. So that's infinite descending chain. Okay. So this is the proposition, which gives us a characterization of Artinian modules, and finally, maybe the main theorem about the matrix duality, or maybe let me put matrix here, but as I said earlier, sometimes if you open a textbook about the matrix duality, you will find one huge theorem, maybe with 5 statements, sometimes with 10 statements that include everything. The case of finite length modules, the statement that the endomorphism of the E is the completion of R, maybe something else, maybe something like this. And of course, it will have the following 3 statements. So let S before R M be a local, so be a complete local Noetherian ring. And then we have the following 3 statements. So first, if M is finitely generated, or Noetherian if you prefer this terminology, then M check is Artinian. So this kind of duality is switching Noetherian and Artinian. So 2, if N is Artinian, then N check is finitely generated. And 3, well, let me say it like this: Artinian and finitely generated modules are irreflexive. Not to confuse with the standard reflexive, which will be R reflexive. Okay, so we've done a lot of preliminary work, so now this has to be very easy. Maybe I can live with this as an exercise, it's that much easy. So let's look, for example, at 1. What it means that M is finitely generated, it means that we can write something like this, right? Now you apply the duality home into E, and then you get the M dual is a submodule of the E to the N. That's it, that's the proof. Now for 2, it's more or less the same. Since we know that it's Artinian, by what we proved just before this, we know that this Artinian module N can be embedded as a submodule into E to the N. Again, you apply duality, and you'll get this is N. Okay, so 3. Well, let's start with the situation where M is finitely generated and show that this is reflexive. Well, this is find the generated module over Noetherian ring, so I can write the presentation for the module M. Right? And then I apply to this presentation the double duality M double check, or M double check, and M double check. Well, for R, I already know that this is an isomorphism. Well, I know this for the ring, right? But since this is complete ring, but if I take finite sum, it goes to the same finite sum of the jewels. So it's these two maps are isomorphisms. Hence, the canonical map from the M to its double dual is an isomorphism, say by lemma. Okay, so this finishes the proof of the three for find the generated modules. Now let's take M to be Artinian for finitely embedded. So then I do the following. First of all, I know that there is a monomorphism from the N to its double dual, right? And then there is some quotient. Let's call this quotient Q. So the goal was to show that the Q is 0. So let's apply duality one more time. I'll get Q check, N with 3 checks, and N with a check, 0. Well, I claim that this map between the N with the 3 checks and N with the check is an isomorphism, right? If this is an isomorphism, then Q check is isomorphic to 0, and Q is isomorphic to 0. That's all we want. The little thing to think about is why we have an isomorphism here. What's
This
it?
M is finitely generated. And M check is finitely generated, and then we already proved it.
Yeah. Well, you need to say something about the maps, right?
Yeah, that's true. Because we know that there is isomorphism, that's why it's
Yeah, it's kind of the map that goes in the other direction, right? So from the double dual of the N check to the N check. But nevertheless, we know that N check is finitely generated module. Right? So we know that this module is, at least we know that this is by some map, is isomorphic to the N check. Right? And then we have an endomorphism of finitely generated module, which is an epimorphism. But it's not automatically an isomorphism. This is one of the parollars of the Nakayamas lemma. If you forgot the statement, look is in the notes on the Google Class.
Actually, why we do something for n if we have proved that the map from M to M double check is isomorphism?
I'm proving that this will be a reflexive module when n is Artinian.
If the module in 3, you stated that if the module is finitely generated and Artinian, then
No. You see, this is a tricky way to formulate this. Is Artinian and finitely generated modules. I mean, like a class of modules, not together. So you separately can take Artinian modules, they are irreflexive, or finitely generated, they are irreflexive. Of course, if they're together, then it's just a finite length that we already know. But you can see this proofs works for finitely generated, I have a separate proof, and then for Artinian, I can reduce to this proof.
yes. And why the map from N to N double check is a monomorphism?
That's we proved last week that I think even in more general situation, if you take a double Homological injected co-generator, you'll get a monomorphism.
Yes. Okay.
Well, because what would be in the kernel would be some element such that any map from the dual to injected co-generator is 0, so it's not just not possible to have no zeros assurance. Okay, so that's the proof of the map duality. And now let's do the Gorenstein rings. So the last section of this chapter. Definition, again, for two parts, for local Noetherian rings and for general rings. A local Noetherian ring R, M is called Gorenstein if the injective dimension of R is finite. And two, a Noetherian ring is called Gorenstein if the localization, any maximal ideal, is Gorenstein. Gorenstein for any M in the spec M. Okay. So,
What the problem to just say that the ring, any ring, is Gorenstein if, well, commutative ring is Gorenstein when injective dimension is less than infinity?
no, I think this is just two different conditions. So sometimes what I call Gorenstein is called locally Gorenstein, and what you said is that we call something called globally Gorenstein. And of course, if you have globally Gorenstein, you have globally Gorenstein. This is trivial, but is it true in the other direction? That's the question. Maybe if you assume that the ring is not real, this is true, but I'm not completely sure about this.
To be true that there would be finding many maximum modules, but otherwise, essentially, simply
Yeah, but
Yeah.
I'm just,
At the moment, I believe this is not true, but I don't remember the counterexample.
maybe their results can be finite, but they can have growing number of non-zero.
Yes, so there could be unbounded,
Yeah, unbounded.
unbounded the ejective dimensions for the maximal ideals. It's what Nagata's counterexample for the dimension. We could have a Noetherian ring, right, of infinite full dimension. Any localization has finite full dimension. Any local Noetherian ring has finite dimension. But if you drop the local assumption, then it is possible that any prime ideal is a finite full dimension, but there is no bound for all the prime ideals. So I think that something like this would happen. Maybe I can think about this and give you this as a problem in the study. To prove that something is counterexample. Okay. Yeah, so first of all, I want to prove several rather trivial statements. So first proposition is kind of analogous to what we have for maximal point Macaulay. If I assume that R is Noetherian, if R is Gorenstein, then any of its localization is Gorenstein. So let's take S inside R to be a multiplicative subset. Then localization of this multiplicative subset is Gorenstein. So the beginning of the proof is more or less the same as the proof for maximal point Macaulay. We just reduce, so take a maximal ideal in the localization. Notice, say this is maximal ideal. Notice that if you localize at S and then you localize at this maximal ideal Q, this is the same as localizing R at P, and this is the same as localizing R at the maximal ideal. and then localizing at P. So here, P is contained in some maximal ideal, and the Q is just the localization of the P. We can always, for any maximal Q, we can always find such P. That's the same as for maximal Homological. So we can reduce everything to the localization. Well, we can reduce everything to the assumption that R we started with is a local ring, in this case Rn. But the rest of the proof is even easier if you look at the injective dimension over the localization, then this is bounded by the injective dimension. Yes. And this is for any module M. We prove that under assumption that R is Noetherian, if you localize an injective module, you still get an injective module. If you localize an injective resolution, you still get an injective resolution. Maybe not the shortest one, hence the inequality, but at least we have this. Yeah, that's enough for the proof. Just plug in M equal to the ring. Okay. Second proposition. Kind of standard things you're supposed to check when you work with some class of rings. How it behaves with respect to localization, how it behaves if you take a portion by a regular element.
Excuse me, can you repeat why do we have inequality of injective dimensions?
Well, suppose this thing is a finite number. No? It's the only case where we need to check something. Then M has a finite injective resolution. You localize this finite injective resolution. The localization is exact, hence this is still a resolution. And if the ring is Noetherian, localization of an injective module is injective. So we explicitly construct an injective localization for the injective resolution for the localization.
Thank you.
Okay, so proposition that Rm be a local Noetherian ring, X is R regular, just not a zero divisor. So then we can say that if R is Gorenstein, if and only if R modulo X is Gorenstein.
Yeah, does everyone mean Gorenstein as an like it's injective dimension over himself?
Yeah, yeah, so this is Gorenstein as the, yeah,
That's the
perfect. The proof is again just one line. The injective dimension, if you have a regular element of this function, is equal to the injective dimension of the R over R minus 1. Again, we prove this in general for any plan to generate module. Yeah, I think that was this argument where we used an adjunction to say that the form of the R modulo X will preserve the injectivity of modules.
Yeah, that was.
Yes. So yeah, we will
Just change from sphere.
yeah, maybe we can say, but I don't use this terminology in this course.
Yeah.
Okay, and finally, maybe the most interesting of these three simple propositions. Let's assume, as before, that we have a local Noetherian ring. So that's this thing will be Gorenstein local Noetherian ring. Then R is Homological. This is the first observation. And this injective dimension that we're supposed to be finite, right? It's not just another number that you can, not numerical variant that you can attach to the R, but this is precisely the dimension, the crude dimension of R. Okay.
R is always Macaulay if it's garbage state.
Yes.
This is the statement.
Yeah, so if you take a local constant, then this is going to be. And since both conditions are defined locally, this will be true for any integral ring. And so the proof is just a combination of what we know, right? What we know about the injective dimension of any finitely generated module, right? If this is a finite number, well, we know the bus formula, which tells us that this is the same as the depth of R by the bus formula. And then after the bus formula, we proved inequality that for a finitely generated module of finite injective dimension, the dimension of the module is always bounded above by the injective dimension. So we have this inequality. And finally, the depth is always bounded by the dimension. So this that we discussed for inequality. Now, compare this one equality and two inequalities, and you get all these numbers are equal. Right? So in particular, the depth is the same as the dimension, and is the same as the injected dimension of the ring R. So that was easy statements. Now here, which is also not hard, we're going to characterize Wallenstein rings in dimension 0. So let Rm be a local Artinian ring. Then the following are equivalent for conditions. So first, R is Wallenstein. 2, R is injective as a module over R. 3, R is isomorphic to the injective hull of the residue field K. And condition 4, the circle of R is one-dimensional. So the circle of R is isomorphic to the K. So these are 4 ways to characterize zero-dimensional Wallenstein rings. Proof. Oh, the fact that 1 implies 2, I think is more or less immediate, right? This is a ring of dimension 0. We know that the injective dimension by this proposition is the same as the dimension of the ring. So let me say that the injective dimension of R is the is the crude dimension. So this is just dimension of R, which in this case is 0. Hence R is injective. So that is easy. Now 2 implies 3. Yeah, so here we need to do something. So I know that R is injective, right? So first of all, I already know the structure of, first of all, I can notice that R as module is indecomposable. Okay. Do you know why a local ring is indecomposable as a module?
Что? Как по-русски будет
Неразложимый.
Неразложимый. Нельзя представить в виде суммы двух. Прямой суммы, да. Ну или большего количества.
Но если оно индексивное, то, скорее всего, если можно, там...
Если локальное кольцо всегда индекомпозабл.
Да.
Потому что если бы оно было в виде прямой суммы, то его простые идеалы были бы вида, что все элементы отсюда плюс какой-то простой здесь, или наоборот. Тогда максимальный тут был бы и здесь было бы хотя бы 2 максимальных.
Один из способов это доказать, да. Ну, вообще, наверное, много способов это есть доказать. Там можно на идемпотенты посмотреть, там разложение придет к тому, что у вас есть нетривиальные идемпотенты, а такого не может быть в локальном кольце. Okay, so anyway, so any local ring is indecomposable as a module. Now, this is injective, right, and also indecomposable. And earlier when I discussed injective modules, I classified all the indecomposable injective modules. So I can say that this R is isomorphic to the injective hull of the R modulo P for some P in the spec of R. So I only need to show that this P that I have is precisely the maximal ideal. So the observation is the following: that any zero-dimensional ring is Cohen-Macaulay, so the depth of R is the same as the dimension of R is 0. So the set of the associated primes of R is just singled on this one element, which is the maximal ideal, right? But the associated primes of the, let me maybe write this, associated primes of the injective hull is the same as the associated primes of the R modulo P, which is just this prime ideal P, right? Hence, P is equal to M.
Can't you say that in the linear ring, as any prime ideal is maximal, and hence P is equal to M?
Yeah, I guess this is much better. If you don't have any other prime ideals, yeah.
What do you say?
What you're saying is just this spec is just one point, this element M. So you don't really need to do this. If this is some prime ideal, this is necessarily maximal ideal. Okay, some simplification. Okay, and now let's see that 3 implies 4. Right, so I know that R is isomorphic to the injective hull. Oh wait, let's look at the circle. Circle of R can be computed as the home from the K to the R. Right, so then, since I know that the R is isomorphic, in this case, to the injective hull of K, this is this one, and we know that this is isomorphic to the K. So the circle is one-dimensional. So finally, 4 implies 1. We know that the circle is one-dimensional. We want to prove that R is foreign string. So the type of the ring R, we know that this is dimension of the circle of R, right? So this is zero-dimensional case. And the dimension of the circle is 1. So ring R has type 1, right? This is faithful and finite length, of course. So we just use what we proved before to conclude that R is isomorphic to the injective hull. But that's what we want, right? So we want finite injective dimension. Well, this is finite injective dimension, namely 0. Okay, so I think it's time for a break.
А можете напомнить, как мы получали, что доказательство первого утверждения на левой доске? Откуда мы получали, что когда мы факторизуем по регулярному элементу, у нас инъективная размерность уменьшается?
Показать сейчас.
Это в лекции 7 рецепт не доказывали.
Ну я знаю, я открыл, я просто не понимаю. По своему
Там некоторые доказательства, там не должно быть очевидно было.
Полная лекция, кстати.
Написано лекция.
Лекция сегодня, прошлая лекция.
Ну вы должны добавляться лекции. Ну это прошлое.
А,
Они просто, почему размерность не больше не размерности? Почему размерность не больше не размерности?
Это было такое утверждение, которое отдельно доказывалось, была формула массы, и следующее после него было это утверждение.
Ну, такая мемка про то, что это, если у нас локализируется кольцо, регуляр R, там регулярный элемент, x равно
Да, это правда.
вот эта вот вещь выполняется. Что у нас x и плюс 1 равен.
Может быть, это не очень оценить, то, что вы не знаете литературу, просто то, когда я готовился к лекции, то, что я понял, надо взять учебник по Сумура, и там есть начало,
это вопрос
и продолжение его пользы. И там вот эта теорема, которую сейчас буду доказывать, доказывается, если там совсем левым, страниц почти что там 10, что 8, что в этом. А потом есть продолжение про инъективные всякие вещи отдельно. То есть, когда Эйнштейн закончился, начинается структура теории инъективных вещей, там всякие формулы массы, в самом конце. Надо для того, чтобы историю поставить, тогда вот из этой теоремы, которая на 10 страниц доказывается, надо выделать все, кроме одной страницы. На самом деле полстраницы даже. Все остальное становится очевидным, более-менее. Я говорю, что я пытаюсь на лекции делать.
А сейчас будут у нас чем лекции или сегодня тоже?
Лекция уже так.
А где сегодня?
Нет, сегодня.
Что-то нет совсем. Или он пришел не проводить и на этой
Знаю,
неделе,
но-
и на следующий.
Он знает, что он заболел.
А можешь спросить? Да. Сань, вот здесь вот это home, ну типа обычный home или home комплекс?
Ну, комплекс, конечно, какой-то.
Не, в том плане, что это, понятно, что это home комплекс, но это комплекс home, ну, это home дефис комплекс или
Да,
home в категории комплекса.
комплекс.
То есть дефис, окей. Вот в третьем мы определяем point Маркович как бы только для Ньютона конец. Это Ньютон получается.
Да, конечно, да.
И вот здесь вот 12, где там вот этот цикл implementation, это как R1 или как R-же, да? Какой Маркович спрашивается.
Я здесь уже сколько наколено с кольца.
Ну, то есть как R-же. Ага.
У меня будет автомат 20 semester.
То есть ты у кого-то красный, я реально понимаю.
Теперь помню, кто-то спрашивал вопрос на прошлой неделе, можно ли там теореме Барса про характеризацию инъективности при помощи суммы инъективных ограничить счетными.
Да, да.
Вот, можно. И это будет упражнение в тезисе за домашнее задание.
Отлично.
Возможно, мы сегодня немножко пораньше закончим. Я просто думаю, может это займет, ты говоришь, что я больше времени, может даже больше, чем одно занятие. Но судя по всему, осталось мне 4 вроде страницы. Я точно должен успеть, возможно, там останется 10 лишних. Может быть, кстати, имеет смысл сказать, неофициально, так в перерыве, как вообще можно думать про гейнштейновость. Ну вот вообще, я прошу на своему личному опыту довольно важно понимать двумерный случай. Вот, потому что любой другой случай свойства к двумерному, если просто его характеризуется по какой-то регулярной последовательности. Это особенно интересно понимать, что происходит в размерности ноль. Вот, с точки зрения полиморфальности, я такую задачу формулировал в втором домашнем задании. Есть упражнение, что нормальный концов полиморфального, тогда это когда его длина совпадает с кратностью. Характеризация полиморфальности в размерности 0. Но вот эта вот характеризация Эйнштейновости в размерности 0, но, возможно, вы не сразу видите, как это связано с тем, что вы уже знаете. Например, вы знаете такие вещи, как по гречески помните, допустим, с Пуанкаре, например, гомология, да, например, гомологии, на форме. Вот. Вот это вот утверждение, что это алгебра, точность Пуанкаре, конечно, верно, определенная, это точность утверждения, что это алгебра Эйнштейна. Нормерность, Эйнштейновость, ну, плюс еще программированность, Эйнштейновость, это точность алгебра Пуанкаре. Может попробовать доказать упражнение. Не знаю, почему я давать задание на упражнение, потому что вроде как не обсуждаем программирование голосовое. Не знаю, давать задачу программирования просто не учится. Но мне кажется, это просто важно сделать. Что в топологии мы как бы с этим работаем, только совсем примерно.
Кратность мы определяли на курсе внутренней алгебры, да?
Да.
Можете повторить, это как-то связано с точностью Пуанкаре Эйнштейна?
Да.
Можете повторить, почему?
Ну, берем градуированную алгебру. Ну, то есть, в Пуанкаре она в градуированном случае, да? Значит, берем градуированную алгебру, конечно, мерную. Ну, то есть, у нее есть какие-то какое-то количество, конечное количество компонентов, набивают одномерно, ну и соответствующие там свойства, что там компонента ита, она изоморфна двойственной по пространству к минус и. Отлично, алгебра с точностью Пуанкаре. Движение, которое сделано следующее. Возьмем градуированное кольцо, ну, скажем, даже на поле для простоты. Но с такими свойствами, как было сказано, что оно очень мерное конкретное пространство, градуированное, да, и, соответственно, если оно, конечно, мерное конкретное пространство, круговой размерности оно 0. Вот я утверждаю, что свойство быть алгеброй Пуанкаре — это свойство быть Эйнштейновости. Быть Эйнштейновым. Одно и то же просто.
На нем у меня такой вопрос.
Осторожно, что просто есть у вас какие-то компоненты изоморфно к n-и двойственны на поле. Ну, то есть это ровно та двойственность, которая возникает у вас, как гомология хорошего полученного пространства.
У меня вопрос. Есть какое-то объяснение вот этой вот как-то аналогии, которая постоянно проходит между градуированными локальными границами?
Я не вижу, почему это аналогия.
Ну,
Движение, которое я сделал, такое: если вы что-то можете доказать одного локального кольца, вы, скорее всего, можете доказать для градуированного, и это будет проще и лучше.
почему?
Потому что градуированное кольцо явно проще установить.
Да,
Ну, там как бы вы можете разбить. Ну, это хорошее градуированное, то есть разумный смысл, то есть ну, там, в принципе, можно устроить область в себе жизни, можно сказать, что у вас нулевая компонента — это локальное кольцо, а потом над ним еще у вас есть какие-то остальные компоненты, да, это будет все включать вместе. И, ну, просто обычно, когда люди размысливают, что это типа нулевая компонента — это поле, все остальные компоненты — это, конечно, мерные пространства. Разумная ситуация, то есть, конечно, да, несколько переменных, это будет соотношение, но вот получается вот нечто такое. Да, ну и понятно, что оно лучше устроено, чем произвольно локальное кольцо. Ну, потому что по многим причинам у вас есть вот эти просто конечномерные, одномерные компоненты. А конечномерные эти компоненты градуированные, это просто упрощает вам жизнь в очень многих ситуациях. В каком смысле это получается как бы посередине между градуированной алгеброй и конечномерной алгеброй. Значит, это можно постоянно использовать. Ну и есть всякие занятные утверждения, здесь тоже смотреть на упражнение. Если вы говорите локальное мертвое кольцо регулярное, в смысле, что ложная размерность равна. Ну, то, что мы про него много можете сказать, их довольно много бывает таких. А если берете градуированное, можно если компоненте 0, все остальные К, компоненте, все остальные, конечно, мерные, то есть просто структурная теорема, что если оно регулярное, то это кольцо конечно, чуть другого плана. В этом смысле там регулярный очевидным образом устроен, это очень удобно. Ну, потому что на самом деле как получается основной, получается как фактор регулярный, разумеется. Ну и какие-нибудь другие еще вещи, не знаю. Берете вот любую алгебру, конечно, порожденную, да, это фактор смысле, потому что
Да, да,
следующий,
да.
но для локальных колец нет такого движения. Для локальных колец ближайшее, поэтому это вы переходите к полным, да? А для полных есть такая структурная теорема Поэна, что любое полное,
Ты?
да, что любое полное локальное зеркальное кольцо – это фактор кольцо от формальности между соотношения. То есть локальная мертвая ситуация такая чуть посложнее, чуть попроще, полная, но она все равно отличается от градуированной. А градуированная это еще более приятно.
Ну, то есть этимология направляет что как бы в одну сторону, из-за того, что есть фильтрация, естественно. А там есть фильтрация, которая лучше.
Но эта фильтрация не то, что идеально работает.
Да, как бы, ну почему если
Мы
что-то...
смотрим, если мы перейдем к ассоциированному градуированному объекту, да? Ну, там, вот Эйнштейн, например, это не сохраняет.
Да, но я хотел, наверное, что-то вроде того вопроса движения про то, что если здесь движение в двух локальных колец, то его, есть какой-то универсальный алгоритм переформулирования его в утверждение для хороших градуированных колец.
Ну, такое есть, но я не думаю, что это может сформулировать в виде какой-то метатеоремы. Типа, если это верно в локальном случае, это верно в градуированном. Обычно всегда пишут, что типа, ну, написано, что это верно в локальном случае. Ну, все то же самое про это градуировано. Просто это так, чтобы от этого избавиться, я такого не знаю. Но обычно действительно так. То есть, там, я, кстати, не знаю каких-то вот, например, когда бы это было не так, что мы смогли доказать в локальном случае, а градуированного смогли перенеслось почему-то. Это очень странно было. Так что в каком-то я на градуированных играх у вас есть всякие разные добавки. Вот здесь там структура теорема, у вас там есть, что там еще есть. А вот, кстати, хорошее замечание. Вы берете вот такое градуированное кольцо, совсем хорошее предположение, которое я сказал, и интересуетесь, что в нем есть такое регулярная последовательность. Если я сейчас правильно помню, ничего не напутал у себя в голове, то это ровно то же самое, что просто набор элементов, между которыми нет алгебраической зависимости.
Набор элементов, которых нет.
Ну, одна, да. Ну, который не удовлетворяет никаких уравнений. Все алгебраически независимо в конце. Соответственно, как бы понятие регулярной последовательности в том смысле становится гораздо более понятным, таким легко трактуемым, интуитивно. Потому что здесь это формальное определение, какие-то неформальные свойства, нам это просто набор элементов зависимости.
Там можем кольцо многочлен просто вложить туда, естественно, с помощью регулярной последовательности получается.
Можем.
Это в каком случае еще раз? Просто градуированное кольцо?
Ну, если там регулярные элементы какие-то есть.
Ну, я хочу говорить хорошее градуированное кольцо, вот это, что я имел в виду, многочленно фактор по каким-то соотношениям, ну или, там, абстрактно говоря, оно связанное, то есть любая компонента это поле, и все остальные компоненты, конечно, верны. Ну, это связанное мертвое, надо сказать, достаточно. Вот. И вот то, что вы сказали, тоже, кстати, довольно интересное замечание, что когда у вас есть регулярная последовательность, вы можете не просто ей идеал породить, а можете смотреть на нее как на способ вложить некоторую подалку в кольцо вектора. И это как бы довольно любопытно, потому что вы можете спрашивать, как у вас свойства от этих. Это, кстати, называется мертвая нормализация. Соответственно, вы можете спрашивать, как у вас свойства этого отображения колец связаны с тем, что это регулярная последовательность. Вот, так как в локальном случае нельзя просто взять любую регулярную последовательность и ассоциировать с ней некоторое кольцо. Вот. Требуется некоторые дополнительные слова сказать, но вот эти слова во втором задании, там последняя задача, за которой глава обещается, там они сказаны. Вот эта задача там, в любом случае, она становится еще более приятной и еще более полезной. Поэтому вот так, в первом случае в каком-то смысле проще, но и он напрямую связан с алгебраической геометрией. В смысле, что вы проще берете. Но то, что здесь на локальном кольце берете сверху, ничего не изменится. Ничего не дает.
Да, это самое удивительно, то, что изучение локальной ситуации, изучение глобальной коллективной ситуации, это очень похоже на вопрос.
Ну, вот они просто очень удивительно, в каком смысле градуированная ситуация это частный случай, там у вас есть, не знаю, по-русски называется релевантный идеал, то есть все, кроме поля.
Да.
Но это как бы единственный максимальный градуированный идеал, который у вас есть. Поэтому градуированная ситуация, она градуирована локальная.
Да, но геометрически совершенно ничего. То есть как так получилось, что есть локальная ситуация, есть глобальная предельная ситуация, и глобальная предельная ситуация даже лучше, чем локальная.
Ты видел проективное пространство? Ну, это картошка почти.
Ну, вот что, я что-то там не совсем.
Смотришь на него?
Okay, so now the goal of the rest of the today's lecture is to give you several characterizations of the Gorensky rings. I think it will be something like 8. And the Gorensky rings has more characterizations. 2 of them I'm going to give you as an exercise in the assignment 3, and probably there are more. So you will see 10 in this course, but I'm pretty sure there are more than 10. So, theorem. Let me say that this is theorem of the bus. So let Rm be a local Noetherian ring. Let me fix n to be the dimension of this ring. Then the following are equivalent. As I said, there are many equivalent conditions, but I want to separate them into different theorems. I think it's easier to understand the proofs and follow the proofs if you separate the conditions. So first condition, R is Gorenstein. Second condition, that the bus number mu A of the ring R is 0 for any I greater than n. Let me maybe add as a reminder what's the bus number. So in this case, since there is no first argument which is supposed to be prime ideal, this is just the dimension of the residue field of the X I K R. Just a reminder of the definition of bus numbers. So all of them are 0. And condition 3, that there is a 0 bus number for some I greater than n. So if at least one number is 0, then the ring is Gorenstein. Proof. Well, of course, 1 implies 2 implies 3 is clear. Well, 2 implies 3 is definitely clear. Why this is clear that 1 that the ring is Gorenstein implies that all these bus numbers are 0. Yeah. No. This is finite injective dimension. Ring is injective if you have Artinian situation, so 0-dimensional situation. In higher dimensions, this is just a finite injective dimension, and dimension is precisely the dimension of the ring. So here, this is dimension of the ring. So after this dimension, all these x are just 0. Okay. So the only non-trivial proof in this theorem is, of course, that 3 implies 1. This is where we need to do something. Okay. What I'm going to prove is the following. So we suppose, just restatement, that the injective dimension is infinite, and show that all these bus numbers of the R are non-zero for any I greater or equal than n. Well, clearly, if I can prove this statement, this implies what I want. Okay, so the proof will be by induction on n. By induction on n, the dimension. So the base of the induction, the case, n is equal to 0. Okay, so if the dimension is 0, I can take R and I can take its minimal injective resolution. So this is minimal injective resolution. Now I know the structure of the minimal injective resolution. I know that. So yeah, as it was mentioned, this is a zero-dimensional case. There is a local case. There is only one prime ideal, namely M. So if I want to understand the structure of a term E with the index I in this minimal injective resolution, and then this is of the form injective hull of the residue field, well, with some multiplicity, and this multiplicity is precisely the bus number. Right? And that's the end of the proof in the dimension 0 case, right? If I suppose that the injective dimension is infinite, then all these numbers has to be non-zero, right? Because if some number is 0, right, then the corresponding term is 0, and this is the end of the minimal injective resolution, which is impossible. Okay, now let's consider case when n is positive and do the induction. Well, we take prime ideal P, which is not equal to the M. And for this prime ideal, we consider two cases. Consider two cases. So first case, if not exactly cases, it's just situations that we need to consider. Well, the first situation is that when you take a localization at this prime ideal, look at the injective dimension, and this is infinite. Right? So then, since we're proving by the induction on the dimension, and this is P is not equal to M, so the dimension of the localization is strictly smaller, we can say that by induction, so then by induction, bus number mu I of the localization Rp is not equal to 0 for any I which is at least height okay, so if you have a chain of primes, say P, which is P0, this is contained in P1, this is contained in some PD, which coincides with the M. So I'm taking just a chain of primes between the given prime ideal P and the maximum ideal M, and I'm saying that the length of this chain is D. Well, we can notice immediately that the D plus the height of P is less or equal than N, the dimension. Okay, now we use one of the statements that we proved before, the statement of vanishing or non-vanishing objects. If the xi are modulo P M is not equal to 0, so then if well, we can look at the x with the index I plus 1, some R modulo Q and M, and this is also not equal to 0, so and P is contained in the Q. So I need to say that there is Q such that P is contained in the Q in a strict way. So that was a technical statement maybe 2 weeks ago. Now, from this I can derive the following: if the bus number with the index I of the R localized at P is not equal to 0, So then, by choosing some prime ideals, so over P, then over Q, then etc., continue doing this, then you can say that X I R modulo Pn is not equal to 0 implies that the X I plus D between K and R is not equal to 0.
And this is just mu I plus D. Yeah.
No. Yeah, sure. Yeah, that's the conclusion, yes. So the conclusion, so I of R is not equal to 0 for I, which is at least height of P plus D. By the previous line. So the last observation is that this height P plus D is smaller than n. Or no, less or equal than n. And this is enough. Okay, so this is the end of the first case, or the first situation that we need to consider. Then there is the second situation that we need to look at, and this situation that if you look at localization, look at the injective dimension of localization, and this injective dimension is finite, right? And I can say as well that this is for any p which is not equal to n. So you see what I'm going to conclude, that if I can find such prime ideal which is not equal to n, such that localization of this prime ideal is infinite, then I can conclude what I want, that all these past numbers are not equal to 0. Otherwise, the situation I need to consider that these injective dimensions are finite, right, for any prime ideal which is not equal to n. This is the second case. If the first is not satisfied, then we have the second. Okay, so in this case, use what we know. The dimension of the localization is less or equal than the injective dimension. Okay, this is just what we've done before, but for the local rate RP, which is equal to the depth RP, which is less or equal than the dimension. So, as before, all these numbers are the same. They're going to be essentially just the same argument as before. Okay. Now, if I look at the x I over R localized at P between the residue field K of P and the localization RP, so this is isomorphic to 0 for any I greater than the dimension of the RP. Right? So we see that the injective dimension of the RP is precisely the dimension, so we have this. Okay, but recall that general bus number for prime ideal, so P and M, it was defined as the dimension of this X group. So X I over RP between the residue field and yeah. I'm writing M here, but I'm really going to use this. For the RP. Maybe let me just use the argument RP here everywhere. Okay, so we have this vanishing of the general bus numbers. So the this is again, this is 0 for any I greater than the dimension RP. Okay, so now I think this is the interesting part. I claim that from this observation I can say that the mu I of R is not equal to 0 for any I greater or equal than the dimension. So the dimension which is just n. Right? So I derive the vanishing of all these mass numbers for any prime ideal except the maximal ideal. And I'm claiming that from this I can see that the bus number for the maximal ideal can be equal to 0. Do you see why?
Probably it's from the same computation like in the
Like this?
like this here.
No. So remember that I have the assumption, I work on the assumption that the injective dimension of R is infinite. Right? So I know that all these bus numbers for P which is not equal to M are 0. What if at some point I get this number to be also equal to 0? And these are exactly the multiplicities and the minimal injective resolution.
Then
So I'll get a finite injective resolution. So let me maybe write this argument on the other whiteboard. So the explanation for this last implication. Otherwise, for minimal injective resolution, let's say we have E with the bullet of R for infinite injective resolution. We have EI of R is a direct sum over the prime ideals in the spec of the R, injective of the R modulo P, which is taken with multiplicity, which is the bus number. Right? So, and we have this, and if there is, say, I0 greater equal than n, such that the mu I0 of R is equal to 0, then the corresponding term in the minimal resolution is 0. It's supposed to be I0, not T0. Right? All the multiplicities that this term will be 0. Hence, this whole term is 0. Hence, we constructed a finite injective resolution, which is a contradiction. So, injective dimension of R is finite, and that is a contradiction. That's the explanation. Okay, so with this explanation, we've done with the proof of the first several characterizations of the Gorenstein rings. Okay. Questions? So, next here, which is taken from the same paper by us. So the assumptions are the same. So that our M be a local Noetherian ring, and is the dimension of this ring, then the following are equivalent. First, R is Lorentz-String. Second, well, let me formulate like this. Mu of R is the delta In. Do you understand what I mean by this?
It's
Simultaneous.
Yeah, so just saying that these bus numbers, if I is equal to the dimension, this is 1, and all other bus numbers are equal to 0. 3. Just a generalization of this. The bus number for some prime ideal P and the ring is equal to the delta I height of P. And now this is for any prime ideal in the spec of R. So in 2 this is only for one prime ideal, for maximal ideal, and in 3 this is for any prime ideal. Okay. So I think this is a little bit easier than the previous theorem. Probably the only non-trivial practice with that one implies 2. Yeah, so if you know that R is Lorentz-String, I want to compute explicitly all the bus numbers for the maximal ideal and see that this is the answer. Well, first of all, we can say that R is Cohen-Macaulay. We observed this before, that any Lorentz-String ring is Cohen-Macaulay. And so, since this is Cohen-Macaulay, xi between k and r is equal to 0 for any I less than n. Do you see why this is true?
By definition of depth.
I would say by the Lewis formula for the depth.
Yeah, okay. That's true.
So this is by definition of Cohen-Macaulay that the depth of R is precisely the dimension, right? Plus the Lewis formula.
What does Rees formula states?
Well, Lewis formula states that you can compute maybe I write it here. You can compute the depth of a finitely generated module as the infimum of the set of I such that xi k m is not 0. Since you know that this infimum is the dimension before all these things. Yeah. Yes, well, sometimes people even take this as a definition of Cohen-Macaulay. Ring is Cohen-Macaulay, you have this vanishing. Precisely, that's the right word. Okay, so when we try to compute these bus numbers, there are kind of 3 cases. There is this case when I is less than n, I is equal to n, or I is greater than n. Right? What if I is greater than n? Well, clearly this is 0, right? Because R has injected dimension, which is just n. So clearly, mu I of R is 0 or I greater than n. So essentially, there is only one interesting situation: is when I is equal to n. So we do it as follows. Let x, which is x1, x2, xn, be a maximal R sequence. Be a maximal R sequence. Now we know that this maximal R sequence has n elements, the same as the dimension, since we know this Cohen-Macaulay situation. So then, for a regular sequence, we have the following formula, that the x, now with the index n, this is what is interesting for us. So x, r, k, r, that could be any module, but let's apply this to the, well, we need to apply this to the ring R. So this is isomorphic to the home over R, K, R, this regular sequence.
It can be, it should be a module such that X bench, such that X belongs to the annihilator of the module, right?
For this regular?
Yeah.
Well, and no. Well, I would say that this is just a regular sequence for the module. Then you have this regular. That was in the proof that on the theorem that you were saying that this is trivial, and I was saying that it's not completely trivial, and I derived this regular. Okay, the step by step.
It's weird.
Yeah, but anyway, so we proved something like this with the maybe second or third lecture. But now, what we can say. So this is the x that I'm trying to compute. I want to understand this is just isomorphic to the k, right? So now I see that it's isomorphic to this home. Well, the interesting step is that I can say that this is as well isomorphic to the home over the ring R modulo this regular sequence, again, from K to the R.
And that was the thing I was referring to, I'm sorry.
Right? So you agree that these two homes are the same, well, because K and R modulo modulo this regular sequence is annihilated by this regular sequence. So everything is in that form is automatically in this form. Okay, but now this is clearly just a K. Right? I take a Gorenstein ring, I take a maximal regular sequence, take a quotient. We know already that this is still a Gorenstein ring, but now this is of dimension 0. And so I'm just saying that the circle is one-dimensional. So for this, I need to notice that this is Gorenstein. Dimension 0. Okay. That's I have some additional real computation to prove this, but I don't think that I need anything. So I'm computing this home. I know that this is circle for this ring, and this is zero-dimensional Gorenstein, so this has to be key. I think that's the end of the proof that one implies two. Okay, now let's see how 2 implies 3.
Just localization.
Yeah, so all we need to do is just look at the localization. So the bus number for prime ideal P and module which is R. This is dimension of the xi over rp, k of p are localized at p, and right, we will want to compute this bus numbers, but the only thing that we notice that this localization is Gorenstein of dimension, well, which is precisely the height of p.
But wouldn't it be 1 implies 3, not 2 implies 3?
1.
Like in 1 we have the RS Gorenstein, and in 2 we don't actually have it yet, do we?
Yeah, that's true. No,
Wait, yeah, so it's just maybe,
yeah, but actually.
maybe this is not the right way to say it. Yes.
So we could just say 1 implies 3, and 3 implies 2 trivially, and then it's good,
Я
right?
No.
Ну, а как мы из второго первого видел?
No, I'm just we
Не,
would.
ну ладно, это да, это правда.
I mean, yeah, maybe we should just switch the order. I mean, this same argument shows that 1 implies
Yeah, sure. What I just said is immediately implies that 1 implies 3, yes.
Yeah,
But
And 3
From
plus 2
2
plus
knows
1.
the form of minimal injective resolution. And
yeah, well,
Мы же знаем на самом деле T, то есть это не важно, конечно, 3 или двоек. То есть с добавлением локализации это доказательство есть 1 T из 3 через 2.
Ну,
I still think that there's a hope that we can derive from 2, 3. Just need to think about this for a second.
Do we need actually? I mean, from 2, I mean, 1 plus 3, 3 implies 2, and 2 plus 1 by the previous theorem, right?
So what you say?
2 plus 1 just by...
By the previous
Yeah,
theorem,
by
right?
previous theorem.
Because we have 0 best numbers. So, I mean, we proved the theorem.
The theorem is not very hard, but I still think that I maybe have an argument that 2, what I want to show, that 2 implies 3, right? If I have this for the ring, this property of the past numbers, right? Then I want to look at the past numbers for the localization. Which will be this past numbers, right? Okay, maybe I was wrong. Maybe proving that 2 implies 3 is harder than what you're saying. So let's do as you. Well, this is the proof that 1 implies 3, right? Since we know that this localization is Gorenstin of the dimension which is the height of P. Okay, so 1 implies 2, 1 implies 3. Well, now this is really a little bit weird. So what we need now?
We need to derive like 1 from either 2 or 3. And it's, and it falls from 0
Ну, вот
to
это
Oh.
хотим доказать.
Oh, wait, just.
Тройку выводим пока
Oh,
что.
first of all,
Вы торопитесь, когда-то.
no, I'm just.
Опять решили, как будут рассуждения применяемые вверху.
Okay, 1 implies 2, if we have this. Now 1 implies 3 is kind of a little bit additional. Well, there's something is clear, right? First of all, the 3 implies 1. It has to be clear because we can just look at the structure of the minimal injective resolution, right? Or, well, maybe even easier, I can say it like this. The injective dimension of R over R I can compute as the supremum of the indices of the xi between k and r, which is not equal to 0. That's another statement that we proved when we discussed injectivity. Yeah, but anyway, so this is how 3.
Yeah, but we need to imply something.
Well, if you want to go from 2,
That's previous theorem, maybe.
yeah. So if we want to go from 2, if we have a lot of mass numbers after the dimension which are equal to 0. So for example, this implies 1 by previous theorem. Is this enough?
Well, it should, because all you can sum up all the illustration is enough.
Не, ну типа из единицы вывели тройку, из тройки двойку, элементарное рассуждение.
Строй. Yeah.
Из двойки в единицу.
Из 2 в 1 можно использовать то, что написано где из 3 в 1. Вот это.
Да, все,
Тоже можно.
достаточно.
Well, but anyway, so Do you agree that what we have already is enough to finish this theorem?
Я думаю, что так, что следствие в таком течении достаточно.
Okay, so let's derive a corollary from this statement. Let R be a Gorenstein local Noetherian ring, where n is the dimension of R. So then the minimal injective resolution of R has a very specific form. Namely, if you look at the term with the index I, you can write this as the sum over the all prime ideals of the height I, and you take the corresponding injective envelopes of the R modulo this prime. Right, so this is more or less formula 3. And finally, another corollary. A local Noetherian ring R is Gorenstein if and only if R is Cohen-Macaulay of type 1. This maybe requires a proof in one direction. So if you know that this is Gorenstein, we already know this is Cohen-Macaulay, and the fact that this is of type 1, this is precisely this computation that 1 implies 2.
What is of type 1?
Well, it means just that the R of R is equal to 1. So this is by previous theorem, condition 1 implies condition 2. So we need to go in another direction. We have Cohen-Macaulay ring of type 1. We want to show that this is Gorenstein. So let X be maximal regular sequence. Maximal regular sequence. Then we know that when we take a quotient, we'll get a Cohen-Macaulay ring. Right, so this is Cohen-Macaulay, and 1, which is the type of the ring itself R. We can also compute this as the dimension of the circle. This probably was the last statement of the previous lecture. So we see that this quotient, which is Cohen-Macaulay, also has one-dimensional circle, and this is zero-dimensional. So the quotient is Gorenstein, and hence R is Gorenstein. End of the proof. So combine this all together, you will get several characterizations of the Gorenstein rings, and I think this all comes from the paper of Bass from 1963, something like ubiquity of the Gorenstein rings, where he introduced all these conditions. And now the goal is to, so if we don't have any questions, I'm going to erase this. So the goal is to give another characterization in terms of the Kazoo complex. Yeah. And for this I need a definition. An associative graded commutative commutative algebra. A is called one-term algebra. If we have the following, so we can write this as a sum of the graded components from one, say, some number g, and the canonical map from the component AI to the home over A0 to the A with the index g minus I a g is an isomorphism.
This time commutative means actual commutative, right?
No, it means the graded commutative.
When we find the G algebras, when it was commutative, it wasn't actual commutative, and then...
Yeah, percent. So it also was graded commutative, this is also graded commutative.
Ah, so it's not actually, okay, I see, yeah.
So all great commutative algebra, it has, ну там, короче, не бесконечное количество элементов, да? Вот, не бесконечное количество градуировок, да? Их всегда конечное количество в этом случае.
No, in this case we have refined the many graded pieces. Graded commutative means that when you switch A and B, you multiply by sign. So this algebra, which is for us, will be algebra of the Kazoo homology. Yeah, this is graded commutative, not just commutative. Yeah, so of course this map that gives an isomorphism, so this canonical map is isomorphism. And the canonical map, of course, here you just take an element and you send this to the following home, and you send B, following homomorphism, you send B to the product of the A and B. So here, with this notation, that is due to Pavlov and Pavlov. So let Rm be a local Noetherian ring. Let's fix notation n to be the embedding dimension minus the depth. So n by definition embedding dimension minus the depth. And the following are equivalent. So first, R is constant. Second, the homology of R is a pointer algebra.
What is ED?
Embedding dimension.
What is it?
It's the dimension of the vector space M modulo the square of the maximalizing. Or in other words, the minimal number of generators in the maximalizing. Okay, and condition 3, that the K-linear map from the homology with the index n minus 1 to the home over K from the h1 1 to the hn r is monomorphism.
Should be
Yeah, okay. So maybe one thing that I need to be said, what's the homology of the ring? Before, when we discussed Kazoo complex, that there was a sequence, right, not a ring. So here, what I mean in the condition 2 is the following. I take M to be generated by a bunch of elements, say maybe some D. So this D is precisely the embedding dimension of the R, right? And then homology algebra of the ring R. This is by definition the homology algebra for the sequence S. It's not necessarily a regular sequence, so homology are not necessarily zero.
It's trivial to see that it does not depend on.
Well, we'll see this eventually, so let's believe this at the moment. Later I'm going to give a proof.
It's kind of liquid,
It's not a hard proof, but
yeah.
I don't want to do this right now. It will be discussed later. So let's fix T to be the depth of the R. And what I want to do, I want to reduce everything to the depth 0. So I can use the prime avoidance to say that M is not contained in the M squared union with the primes which are associated to R. So then I can claim that there is an element y1 which is in the M minus M squared and which is also R regular. So
You say like if it's larger than 0, this whole happening.
what's larger than 0?
You want to
Yeah, so let's say that this T is depth and this is positive number. Right, so then I can find one element y1 which is in the M but not in the M squared. And then I do induction. So by induction,
What are proving? What are proving? What implication?
well, I'm not going to prove this directly, this implication. I'm going to do some preliminary work and then return to this statement, this kind of flow that we're going to do a little bit later. I'm going to do some reductions, then a couple of lemmas. Okay, so by induction on the T is the depth.
Why M doesn't lie in M squared?
Why M is not in the M squared?
Yes.
Well, if M is equal to the M squared, then the embedding dimension is 0.
Yes.
Yeah, and M is generated by 0, so M is so this is a field. Yeah. By induction on M, we construct our sequence, which I'm going to call y1 up to yt. So such that this sequence y is part of a minimal system of generators of the maximal ideal M, right? Because on every step I choose something in the M but not in the M squared. Okay. Well, we have isomorphism of the graded vector spaces, so you can compute homology for the R, or you can compute homology for the R modulo Y. And we also have that the R is Gorenstein if and only if R modulo Y R is Gorenstein. So, without loss of generality, we can work in the situation where the depth is equal to 0. Otherwise, we construct the sequence and take the reduction. So, this claim about the Hawkish homology is something that we proved before. It was when we discussed the quasi-homogeneous properties. Okay. Now, let me fix some notation. So let's say that the K with a bullet and D with a bullet will be this causal complex that I want to consider with the corresponding differential, causal differential. Right, so this X is as before the minimal system of generators for the maximal ideal. And when we discussed Kazoo complex, we introduced maps omega I. Now I want to consider almost the same maps, but now I just want to take the home from the ki to the home kn minus I and the kn. Just to agree with this definition of the Poincare algebra. Well, it's not really important since kn is just isomorphic to R. Up to isomorphism, that's exactly the same thing. And we actually, I think we can even change the definition and put A0 here. Not much of a difference. So, well, maybe there is a problem. So let's keep this definition. Okay. So as before, we can prove the formula that the omega with the index I minus 1 composition with the differential with the index I is up to a sign. So this is minus 1 to the I minus 1. The dual of the differential. Let me write this explicitly. Differential with the index n minus I plus 1. And this is home into kn. But this is what I'm going to call up to a sign the dual differential. Index n minus I. Okay, and I also fix notation and say that the complex with the star, the dual complex, now it will be the home from the Kazoo complex to the Kn. Which again, up to isomorphy is the same as the dual complex before. And omega I induces isomorphisms on the homology from the hi of R to the h with the index n minus I, but with the cohomological index of R. So the cohomology of the R are by definition the cohomology of the K with the bullet and the star.
From what we deduce the third from the bottom line.
This one, this is just a computation, and I think I could have said that with something that we've done before, but I think before I also left it as an exercise. So do this exercise just an explicit computation. So everything is kind of simple here, just stereo algebra is differential.
So this home is just the... Ну вот справа то, что у нас от ориентации, это просто kn и со звездочкой, то есть это та же самая ориентация, что мы определяли.
Yes. Up to some notation, up to some isomorphism, that's precisely the same as before. Okay, so now the key ingredient is to look at this diagram. So I have homology of the ring R. Here I have a map delta I that I'm going to find a little bit later when I finish with this diagram. So this will be home over K from the homology with the index n minus I over R to the homology with the index n of R. Here, this is just the isomorphism omega I with the tilde, and this is h with the index n minus I of R. This will be a map beta I, and here we have home over R h n minus I of R. Okay, and this map is called gamma I. So what are the maps here? So first of all, this delta I is the same map as that we used in the definition of the Poincare algebra. So let me say that this is induced by multiplication. So you can always consider this element from hi as a functional. On this, you just take a product and look at the corresponding homology class. So this is induced by multiplication. So this map is already defined. This is an isomorphism. Now, map beta I assigns to homology class of psi map from the h n I r to the kn, which is defined as following. So you take a class of A and you send this to the psi that you compute on this class. So exercise, check that this is well defined. Okay, well, a little bit we will do an exercise, well, we will do a computation for which you can see this is a well defined map. Yeah, and finally we have the inclusion, so Hn of R is the so-called of the Kn, which is embedded into the Kn. Hence, we can define the vector gamma I as the home Hn minus I of R I. So this last map is just induced by the embedding of the so-called into the Kn. So the computation that the Hn is precisely the so-called of Kn. Again, this is something that we've done before, but I also want to say this is immediately clear. Just look at the definition. You'll get exactly this is homes from the K to Kn. Okay, so these are all the maps. Well, and we also can claim that the gamma I is an isomorphism, right? Well, by the same, we've done something like this. So here, everything, this module is annihilated by the maximal ideal, right? So if you look at any home that lives here, this give you automatically home here, and home here, since this is annihilated by the maximal ideal, give you home here. So this is an isomorphism. So, and the diagram commutes. Again, this is, if you just compare all the definitions, I'm not going to do the computation, if this is an exercise, but if you just look at all the definitions, you'll see that this commutes.
Yeah, gamma I is an isomorphism is.
Well, the reason for this is that the maximal ideal annihilates Hn minus I of R. So, first lemma. So continue to assume that I have all this notation as before. Let me just say that if I also introduce notation for the boundaries, so these are boundaries in the Kazoo complex. So then there is long exact sequence 0, and then we have x1 where we have ki minus 1 modulo the boundaries b I minus 1 kn, and this is mapped to the hi of R, and the map is b with the index n minus I. So this is to the home from hi of R to the kn, and the last is x1 bi minus 1 kn. And this is for any I which is at least 1.
Yeah, may I ask about gamma I? Gamma I is home it's defined like home from something to the map. Yeah, and home over what? Over ring or over?
No, this is well, if you wish, this is over R.
Over R.
Yeah,
but the domain is over K.
As I said, this is not important. So you see this as a module over R, but in fact it's just module over K.
Mm-hmm. So we can just. Mm-hmm.
Yes, so this is the idea of definition of this gamma I. So since everything is annihilated by maximal ideal, yeah, this works. Okay, so to prove this lemma, well, it's kind of more or less immediate homological computations. We will look at the short exact sequence where we have hi of R that sits inside ki modulo bi, and this there is a map to the boundaries with the index I minus 1. So this is just a map which is induced by the differential. And of course, the kernel of such map is precisely the homology. So this short exact sequence gives us the long exact sequence. We have 0, home, bi minus 1, kn. So just take a home into kn. We'll get home ki modulo bi into kn. So then there will be some map sigma I home from the hi of r to the kn, and then we'll get x. So x1 bi minus 1 kn, etc. Well, we will notice that, well, here the sigma I is given quite explicitly, and the image of the beta with the index n minus I is the same as the image of the sigma I. Just a silly computation with the modules exercise. So, but if this is the case, I have the following sequence. I have hi of r. Now I write beta with the index n minus I to the home from the hi of r to the kn. Right, so I just start with the beginning of the beta, and then since the image is the same, I replace the rest by this exact sequence. So then the next term will be the x1 over r from the bi minus 1 to the kn, etc. So to prove the claim of the lemma, now it would be enough to compute the kernel of this map beta that we have here. So let's also fix notation for the cycles. So zi inside ki are cycles. And then we have the following. We have ki plus 1 is mapped by the differential, Kazoo differential, to the ki, and this is mapped. Well, this is just differential that I want, but I want to factor this as a boundaries, and then embedding of the boundaries into the ki minus 1. Okay, so this is just map induced by the differential with the index di. Now suppose I have some cycle psi from the ki to kn, exactly as in this definition, right? So for the beta I, it acts on the cycles, right? So I take such a cycle. So if this is a cycle, it means that the composition of the previous differential and the psi is 0. Now, condition that the cycle psi is in the kernel of the beta with the index n minus I. What it means? Well, I take the cycle, I just by evaluation, I associate with maps on the homology, and I'm saying that this map on the homology is a 0 map. Right? But if this is a 0 map on the homology, it means that say if psi is here, then there is map psi prime, which will be a map from the ki modulo zi to the kn. Right? On the homology, this is 0, so on the cycles, this is 0. Hence, there is a map on the quotient by the cycles.
Мне кажется, что в длинной точной последовательности есть какое-то нарушение с индексами. Там в начале b и минус 1, и в конце b минус 1. Так и должно быть.
Да.
Ну вот в длинной точной последовательности в леве.
But this is not this is not a long exact sequence that comes from a short exact sequence. This is kind of separate computation.
Okay.
So it comes from, I take this short exact sequence, I look at this long exact sequence, I notice that the image of the sigma is the same as the image of the beta, so I replace kind of this beginning by this beginning, and now I'm just explicitly by hand computing the kernel. If I compute the kernel and I see that this is precisely this, then I'm done. So essentially I'm interested in what is kernel and co-kernel of the beta n minus I, and this will be some x.
So this long exact sequence, how it continues? With what?
Well, you can continue this with what you can continue this thing,
It's just
but it's not important again. For the proof, it's just important that for this map beta, there is this term which is x and this term which is x. We're going to see that this gives us some vanishing of the x by homological reasons, so this will be an isomorphism. Okay, so we induce this map psi, and of course this we can identify with the boundaries with the index I minus 1. So what we see now, that the kernel of the beta I is the home of the beta I minus 1 to the kn, namely this is the map psi prime, modulo the maps which can be extended from the boundaries to the whole ki minus 1. Right, so if you can extend this, then the homology of this gives you 0. But of course this home you can just rewrite exactly as the x that you want. So this finishes the proof of the lemma, and why you can do this last computation, well, that is because you just look at the short exact sequence bi minus 1 that is embedded in ki minus 1. The quotient is ki minus 1 modulo ki minus 1, and this gives you something home ki minus 1 kn home bi minus 1 kn, and then there will be x 1 ki minus 1 modulo bi minus 1 to the kn, and then there will be 0, since ki is a free module, ki minus 1 is a free module. So exactly this x is this quotient. Okay. Another number, which is very fun, I would say quite non-trivial. Let Rm be local Noetherian ring. Assume that the depth of R is 0. Assume that the x 1 from K to R is 0. Then R is Gorenstein. Proof. So for the proof, we consider factor home length into R, right? Since this x1 is 0, this is exact on category of modules of finite length. Then by induction on the length, you can prove the following formula. If you look at the length of the home from the M into R, this is the same as the length of M times the length of the home K into R. It's kind of clear when M is just a K, it just immediately follows from you can see that this is true. And then we do the same argument as we've done in the beginning of the lecture. You separate your module finite length into short exact sequence and kernel to kernel. It will be true for the kernel and the quotient by the submodule quotient by its submodule. So it's the same as before, not going to repeat the argument. Yeah, so this is of course for M, which has finite length. Okay, now if the dimension of R is positive, we can observe that the length of the R modulo N goes to infinity when n goes to infinity, it's unbounded. This is one observation, but on the other hand, if you look at the dual, so home from the R modulo m to the n R, well, this is the same thing as the colon ideal 0 colon m to the n. And so in the colon ideal, remember that we have all the elements in the ring that send this ideal to the 0. In general, it would be another ideal, but this is 0. But that's exactly all the elements in the ring which are annihilated by the m to the n. That's the same thing. So we have, for this colon ideals, we have an increasing, so ascending chain, right? So, and this is the situation of a local Napier ring, so there is a stabilization. So stabilizes, this chain stabilizes, and hence the length of the home of the R modulo m to the n R. So this is bounded. And that's the contradiction. On one hand, this is a bounded sequence, on the other hand, this is in an infinitely increasing sequence. So the dimension of the ring R is 0.
In the end of this lab, in the end of this chapter, kernel of beta E should be, or should there be kernel of beta
Yeah,
N
thank you.
minus E?
Yeah, n minus I. This. Okay, so the dimension of R is 0, so this is Artinian situation. Now any finite module M has the property that its length is finite, so it's not just the duality on the finite length modules, this is duality on all finite generated modules, and this is duality on all modules. Hence, since this is an exact functor, R is injective. Okay. So now we've done with this preliminary work. We can return to the proof of the Abramov-Golod theorem. So proof of Abramov-Golod. So if we go from 1 to 2, so now we assume that R is Gorenstein. So then the injective dimension of R is equal to the depth of R, and we reduce to the case when the depth is 0. So Km, which is isomorphic to the R, is injective. And if you look at the first lemma, you can see that the beta I are isomorphisms. There is vanishing of the x in the beginning and the end, so all the both first x are vanishing, so beta I isomorphisms, and so delta I are isomorphisms. And this is of course for any I. Now 2 clearly implies 3, and finally how 3 implies 1? Well, it is given in the condition that the delta with the index n minus 1 is injective. Since the diagram is commutative, we can claim that the beta with the index n minus 1 is injective. And since this is injective, there is a vanishing of the x1 between k0 modulo b0 and the kn. Right, that was exactly the kernel of the corresponding beta n minus 1 map. But we can notice that the k0 modulo b0 is just isomorphic to the residue field k. And of course, kn is still R. So what we have is that the x1 from the k to the r is equal to 0. Which means that r is injective. That's all. And this is the end of the lecture.